Okay, perfect. So welcome everybody. This is Gatorade's presentation for our firefighting aircraft concept, the Phoenix Tanker. So to start out with, my name's Alex Riley, and this is our team. We are 10 undergraduate students at the University of Florida, majoring in aerospace engineering, and we'll each be introducing ourselves throughout this presentation. So to start out with, what was our task? Our task was to create a firefighting specific aircraft that met all of these requirements, and these are all set by the AIAA request for proposal. So I know there's a lot to look at here, so some things to focus on. Our entry into service for our aircraft is 2030. The fire retardant capacity for our aircraft was required to be at least 4,000 gallons with an objective value of 8,000 gallons. Our aircraft needed to be multi-drop capable. That means that it needs to be able to drop 2,000 gallons of fire retardant at a time. Our design radius, which is at the lower portion of the table, with our max payload needs to be at least 200 nautical miles with an objective of 400 nautical miles. And then our design ferry range, that's with no payload in our aircraft, it needs to be at least 2,000 nautical miles with an objective of 3,000 nautical miles. So with this task in mind, what was our approach? Well, our approach was to deliver a fast response firefighting specific aircraft that filled the void between light payload tankers, such as the 737-300 and the C-130H, which hold about 4,000 gallons of fire retardant, and then heavy payload tankers, such as the modified DC-10 and the 747-8, which hold upwards of 12,000 gallons. So with this philosophy in mind, what was our final product? Well, this is the Phoenix Tanker. It has a maximum takeoff weight of a little above 221,000 pounds with a wingspan of 132.8 feet. It is piloted by 2 crew and powered by 2 Pratt & Whitney turbofan engines, which provide upwards of 36,000 pounds of thrust. This propels our aircraft to a cruise speed of 430 knots at an altitude of 35,000 feet. So our payload capacity, again, is 8,000 gallons, and our mission range is a little bit above 1,800 nautical miles, with a ferry range a little bit above 3,300 nautical miles. So this is our final product, but how did we get here? Well, this is going to follow the outline for our presentation. So the outline of our design process first started with the initial estimation phase. So this was understanding some of the general characteristics of our aircraft, understanding the direction we wanted to go in, and then comparing it to historically similar aircraft. So with these initial estimations in hand, we then went into the design phase, first starting with aerodynamics, then propulsion, then focusing on the structure of the aircraft, including the landing gear. We then designed the inside of the fuselage, including our payload system, and finally our tail. So with this fully designed aircraft, we then moved into the analysis phase. So first we started with analyzing our stability characteristics, then the general performance characteristics for our aircraft, and then the cost of that same aircraft. So with all of this in mind, I'm going to hand it over to Jessica for our first section.
Hey, I'm Jess, and I will go over our initial estimations. In this section, we focused on the aircraft goals, historical analysis, and the mission profiles. Next slide. We based our goals on AIAA requirements, intending to meet the mission objectives with a payload capacity of 8,000 gallons and a design radius of 400 nautical miles. We also plan to surpass requirements with a 2,000 nautical mile ferry range and an 8,000 foot balanced field length for given conditions. Next slide. The max takeoff weight of the Phoenix Tanker was estimated to be around 215,832 pounds, with the table at the top showing the distribution of this weight. We calculated the empty weight fraction and the fuel fraction of our aircraft to be 0.416 and 0.137 respectively. Below are 2 graphs used to compare the Phoenix Tanker to other aircraft within the industry. 3 mid-range aircraft were analyzed against the Phoenix Tanker for empty weight analysis, while 3 heavy tankers for fuel fraction at a maximum payload. Next slide. Fuel weight fraction required the use of a mission profile. A 7-point mission profile was developed involving a takeoff, climb, cruise, loiter, cruise, descent, and landing. The 7-point mission profile also included a loiter time of 3 hours. A ferry mission profile was analyzed to account for both missions requirements with a cruise of 2,000 nautical miles. Next slide. Our initial performance calculations accomplish our goals exceptionally well while in agreement with the given RFP conditions. And now I will hand it back to Alex to discuss the aerodynamic design.
Thank you, Jessica. So with those initial estimations in hand, let's move on to our aerodynamic design. So we needed to choose an airfoil for our wing. So we chose to compare 6 different airfoils, and all of these have high lift characteristics. And we wanted to compare the coefficient of lift and the CL over CD for these 6 airfoils. So we used XFLR5 and we inputted the cruise conditions for our aircraft, which equated to a Reynolds number of 3 × 10⁷ and a Mach number of 0.75. So if you look at the graph to the right, this is our output from our XFLR5 simulation. And so you have angle of attack in degrees on our x-axis and the coefficient of lift on our y-axis. So if you look at the airflow, the AH82150A, that's the line in orange, it has an increased coefficient of lift over the other 5 airflows from -1 to 14 degrees. So this is a really big positive. Now let's move on to our coefficient of lift over coefficient of drag. So we can see that that same airfoil, the AH82150A, has a substantially better CL over CD from -1 to 2 degrees, where our aircraft will most likely be operating most of the time. And then it's pretty comparable CL over CD for angles of attack greater than this. So for these reasons, as well as the large thickness of this airfoil, which is beneficial for our fuel tanks, we picked the AH82150A for our wing. Now moving on to our wing design, our reference area and our aspect ratio were determined by our estimated takeoff weight. So the lift produced by our wing needed to equal the weight of our aircraft for stable flight. And then with our wing loading estimation, which is the weight of our aircraft divided by the reference area, we were able to get our actual reference area of a little bit above 2,300 feet squared. So using our designed Mach number of 0.75, as well as the general characteristics of our aircraft, we were able to get an aspect ratio of 7.6. Now moving on to our taper ratio and our wing angles, we wanted to maximize our efficiency at Mach 0.75. So we chose a leading edge sweep of 200 degrees and a taper ratio of 0.25. We also wanted to provide sufficient lift at takeoff and cruise. So we used an incidence angle of 1 degree. We also wanted to avoid tip stall. So we used a twist angle of -3 degrees, which was determined by star-CCM plus software. So here's a depiction of our wing. Now moving on to highlight devices. So highlight devices were needed to increase our coefficient of lift. So if you look at the graph on the right, our clean airfoil with no highlight devices doesn't quite meet our takeoff and landing requirements, which require a CL of around 2.35 and then 2.9 for takeoff and landing respectively. So we need highlight devices. Our philosophy for choosing them was to use the least complex technology that would meet our needed CL. So we chose a slat for our leading edge and a single slotted Fowler flat for our trailing edge. And this was able to shift our coefficient of lift versus angle of attack graph for our wing upwards and to the left to meet those CL requirements for takeoff and landing. So with that said, I'll hand it over to Randy for propulsion.
Yeah, hi, so my name is Randy. I'll be going over the propulsion design. So next slide. So the first thing we need to do was select which engine type we wanted to use. With our Mach speed of cruise being around 0.75, the most efficient engine for this job would be a high bypass ratio turbofan. This also goes in line with our goals of being at high speeds for those quick response times, as well as being able to achieve those low speeds for payload drop with the high lift devices we just talked about. So moving on to the next slide, now that we have the engine type, we need to figure out what the thrust requirements are for our engines. So using 2 different methods with 5% margins, the first one we did was using our initial estimates with that thrust to weight ratio of 0.29. We found that we needed about 33,000 pounds of thrust per engine. Also using this chart on the right of historical commercial aircraft from Boeing and Airbus, we found that we needed roughly 36,600 pounds. So with this, we looked at 35 different turbofans, and then using a series of down selection and decision matrices, we went to go choose our engine. So that'll be on the next slide. Yep. So looking within 30% of the largest thrust requirements that we calculated, we were able to down select from 35 to 6 engines, from which we then decided we did do a decision matrix where we prioritized the efficiency, the weight, and the cost. This ended up resulting in the Pratt & Whitney 1133G. It's interesting to note also that the previous version of this engine was second place in our matrix. So the next slide will show a snapshot of the Pratt & Whitney 1133G engine. This is an engine that's currently in development, set to release in 2024, which meets the RFP of being released by 2028. It will require a scale factor of 7.6%. And with that will be all the requirements set forth with a final installed thrust of 33,400 pounds. Lastly, in terms of the engine, we need to talk about the integration of the engine. So we'll be doing a twin engine layout, which will be potted and mounted underneath the wings. This provides adequate clearance from the ground, as well as provides clean airflow to the engines, relatively low cost method of integrating the engines, as well as easy for maintenance to service on. The thing we designed mainly was the nacelle and the inlet. The inlet was designed for a balance of cruise and mission, as well as takeoff and landings and other scenarios that the airplane will find itself in, with more details on that table on the right. And lastly, for the nozzle, that would just be used from the engine. We won't be making our own nozzle for this aircraft. So next slide, lastly, we'll talk about the fuel and the fuel tanks. So we'll be using Jet A fuel, which is a very common fuel used in aviation, especially for these larger jets. We'll be using an integrated tank design to use the already pre-existing structure of the wings for lower weight. And we will have a capacity of 3,750 gallons with additional smaller tanks to bump that up to 4,500 gallons for those longer ferry missions to reach the objective goals. And now I'll pass it on to Noah for landing gear.
Thanks, Randy. So I'm Noah, and I'll be going over the landing gear design. Next slide. So the first consideration was the landing gear layout. A tricycle gear layout was selected for ground stability, pilot visibility during taxiing and landing, and large crab angles for imperfect landings. Next slide. Next up was the tire selection. Tire sizing was based on the landing kinetic energy and resulted in 2 wheels on the front gear and 4 wheels for the main gears for adequate load distribution. For each wheel on the main gear, it has its own brake for a total of 8 braking wheels. For the front tires, 38-inch diameter by 12-inch wide tires were selected, while larger 40 by 14.5-inch tires were selected for the main gears. Both these tire sizes are available commercially. And then tire pressure was set to approximately 170 psi for best tire life. Next slide. Next is the shock absorber selection. The Leo pneumatic struts were selected due to the large size of the aircraft and their compact nature. Strut sizing was based on FAA requirement for 10 feet per second vertical descent rate, but we sized the struts with reserve based on a 12 feet per second descent speed. Additionally, overall strut size was considered to allow for adequate ground clearance, such as ground to distance or engine to ground distance or tail strike at larger pitch angles. And it's worth noting all minimum clearances are exceeded. Next slide. And finally, I'll go over the landing gear mechanisms. The landing gear retraction is achieved with linkages in the hydraulic system. The front gear retracts forward into the nose while the main gear retracts inwards into the belly. This retraction position was selected so that the gears naturally deploy into their fully extended position due to their weight and drag in the event of a hydraulic system failure. With that, I'll pass it off to Oscar for structures.
Thank you, Noah. My name is Oscar, and I'm going to be going over the structural design of this aircraft. So first up, we have the fuselage. We selected a semi-monocoque structure because we wanted a light aircraft. We also wanted to keep the maintenance costs very low. Now, for the components of this structure, we have frames, stringers, and longerons. The quantity of these was selected based on Boeing 757 because of its similarity in size and weight. Now, the material for these components was looked at in the sense of basically the load distribution across the fuselage. For example, the frames would take the most load, therefore we selected a material that would suffice that. So we selected 70-10 aluminum. For the other components, we selected 24T4. Next slide. So for the structure of the wing, we have spars and ribs, and the quantity of these was selected based off, again, similar aircrafts. Now, we went a little bit more in depth with this, and we actually designed the cross-sectional area of the spars because we know the spars are the components that take the most bending load on our aircraft. So we wanted to take a look at that. And so we designed based on critical buckling, the available geometry that we had to work with. And we also wanted to keep the cross-sectional area as low as possible so we can reduce the weight. Another way that we reduced the weight was through the material selection that we selected for the spars and the ribs. We selected a very high strength weight ratio material. This was the 7075 T6. And for the wing box, we have a material of carbon fiber reinforced polymer because we wanted to keep that strength and stiffness very high. Next slide, please. Now, last thing we wanted to do was to verify that this structure was sound. So what we did was we did 2 different analyses. We did hand calculations and SolidWorks FEA model. For the hand calculations, we first started by analyzing the lift distribution across the wing, and we used the Schrenk method for that. Then we looked at the bending moment at the wing root, and we calculated a factor of safety of 1.8. That was higher than the set factor of safety of 1.5. For the SolidWorks, we went a step further and analyzed the whole structure of the wing. And then we actually ended up with a factor of safety of 1.3, which is a little bit lower than that 1.5 that we wanted. But keep in mind that we also did a more conservative estimate as we only concentrated the lift over 5 ribs out of 26 ribs in the actual wing. So the last thing I want to say is the max tip displacement was 6 feet, and that was common in aircraft of our size range. So I'm going to pass it off to Jimmy now.
Hello, I'm Jimmy. I'll be covering fuselage and payload design. Next slide. So our fuselage length is 131.75 feet. This is from scaling up the jet transport. The fuselage diameter of 16.5 feet comes from our fineness ratio, which is the length of our diameter. We chose that as 8 to balance our aerodynamics. Next slide. We have a ground clearance of 3.71 feet with taking into account the landing gear from the previous sections. We have a nacelle clearance of 7.3 feet to keep any debris from flying into the engines. We also have a taper ratio of 10 degrees to make sure that the tail does not strike the rail, the takeoff as we take off. Next slide. Rear station and cockpit. Our systems will include the VFR and IFR flight with autopilot. We'll have heating for the leading edges of our wings and pitot tubes and whatnot. This is important if the plane is being transported through a cold region or being left overnight outside. We'll have equipment such as radio and GPS installed into the cockpit. There will include a pilot and a co-pilot seating, and the length of the cockpit will be 102 inches to ensure plenty of room for both of the pilots. Next slide. The payload design. We'll have 2 tanks to ensure that in the case of one fails, that we'll also have an entire half of the payload. Each tank is partitioned into 2 so that the payload can shift between as well. Each tank is 25 feet long and has a diameter of 6 feet. Between everything else, when we drop the payload, it'll minimize any type of center of gravity shifting. Next, I'll pass it off to Andrew.
Hello, I'm Andrew, and I will be talking about tail design as well as the control surface design. Next slide. So the configuration of the tail, after looking at common tail configurations, we chose the T-tail configuration. This was chosen as it allows for clean flow to reach the horizontal tail, avoiding any disturbances caused by the high mounted wing in the engine wake, which could reduce efficiency. Also, the end plate effect on the vertical tail increases the vertical tail effectiveness, and this leads to no blockage issues of the rudder, with it being completely clear for any possible angle of attack, allowing for strong directional control. Next slide. So the geometry of the tail, we did this through the volume coefficient method, which was used to provide minimum sizing for the horizontal and vertical tail. Another limiting factor for the vertical tail was that it was required to elevate the horizontal tail enough to avoid any blanketing by the main wing during pitch up situations. So you can see the geometry here to the right. One thing of note is that the vertical tail was designed to endure the stronger forces in the T-tail configuration. So because of this, the aspect ratio was kept low to 1.2. Another thing is that the horizontal and vertical tail were designed to ensure a higher critical Mach number than the main wing. So to do this, we increased the sweep back angle of the leading edge compared to the main wing, and also decrease the thickness of the airfoil compared to the main wing's maximum thickness. Next slide, please. The tail control surface sizing, the rudders and the elevators. So simply, this was done by their span being taken to 90% of their respective tail span, and also their chord being taken as a ratio to their respective tail mean aerodynamic chord. This ratio is taken as 0.32 for the rudder and 0.25 for the elevators. This results in the geometry you see to your right. Next slide, please. The wing control surface sizing. So the ailerons were sized using historical relations between the aileron chord and span to the main wing chord and span. From this, it was found that the largest possible ailerons, given the available space due to the flap configuration, were not large enough to provide sufficient roll control at low velocities. So to supplement this roll control at low velocity, spoilers were implemented. The geometry you could see to the right, the spoilers were designed to cover the outer 45% of the flapped wing area. And now I'll be handing it off to Riley.
I'm Riley, and I'll be going over the stability analysis for our aircraft. Next slide. So before the stability could be analyzed, our actual takeoff weight, as well as our center of gravity, needed to be calculated. Our maximum takeoff weight was calculated to be approximately 222,000 pounds, which differed from our initial estimates of 215,000 pounds, with our primary weight contributing factors being our payload and our fuel. From there, our center of gravity was estimated by taking the moments of each of the respective parts and components of our aircraft to a reference point, which was chosen from 4 feet from our nose tip. From there, the moment arm of our center of gravity was calculated by equating that sum of the moments to our maximum takeoff weight in order to find that center of gravity, which was ultimately found to be approximately 60.2 feet. And this process was repeated for various conditions during our flight, from cruise, either pre and post payload drop, as well as takeoff and landing, with a center of gravity shifting only about half a foot from our two extremes. Next slide, please. From there, our longitudinal stability was analyzed. This was done by calculating the pitching moment contributions from our wings, engines, fuselage, as well as our horizontal tail based on the angle of attack. It was ultimately found that our CM alpha, or our pitching moment coefficient, was calculated to be approximately negative 1.22, indicating longitudinal static stability. From there, trim scenarios were calculated for both takeoff, cruise, and landing, utilizing an iterative procedure in MATLAB to calculate the required angles of attack, as well as the elevator deflections for those various trim scenarios. Next slide, please. From there, our lateral directional stability was analyzed utilizing a similar process by calculating the roll and yaw moment contributions from our fuselage, wings, and engines again, as well as our vertical tail. And it was ultimately found that our roll moment coefficient and yaw moment coefficients were equal to negative 0.56 and 0.34 respectively, indicating lateral and directional stability in the static sense as well. From there, trim scenarios were performed or calculated once again using a similar procedure in MATLAB to iterate for both engine out and crosswind landings to find those required angles of side slip, as well as aileron and rudder deflections required for trim. And now I'll be passing it off to Sophia to discuss our performance analysis.
Hello, I'm Sophia, and I'll be going over the performance analysis for our aircraft. So the first component that we focused on were the range calculations. For our purposes, range can be defined as the aircraft's velocity multiplied by the time it remains airborne. Due to the fact that the aircraft's weight is constantly decreasing as fuel is burned, some simplifications were made in order to utilize the range equation. The values of specific fuel consumption, velocity, and lift-to-drag ratio were kept constant. And once these assumptions were made, the values that are tabulated on the right could be used to calculate our ranges. Our calculated loiter and ferry ranges, mission ranges, do comply with and actually surpass the mission requirement of 200 nautical miles and 2,000 nautical miles respectively. Next slide, please. The second component focuses on the operating envelope. The graph on the right displays the altitudes and Mach numbers that the aircraft can withstand. The three components that were highlighted in the graph were the stall limit line in blue, the Q limit line in red, which maps out the maximum speeds at which the engine can operate for a given altitude, and then the parabolic line of maximum thrust in yellow. It's also worth noting that at Mach 0.75, these stall limits do not interfere with cruise conditions. Next slide, please. The third component focuses on our balanced field length analysis. For our purposes, balanced field length can be defined as the takeoff distance required to clear a 35-foot obstacle in the case of engine failure at decision speed V1, which is graphically represented at the bottom of the slide. The drag component used in our calculation uses both the components of the wings and the skin fuselage, and our resulting balanced field length distance was around 6,500 feet, which complies with both the AIAA and FAA mission requirements that were given to us. Next slide, please. So this final slide summarizes additional performance analyses done on the aircraft, mainly highlighting V speeds. The main ones that we focused on in our analyses was the climb speed, rotation speed, and glide speed. The climb speed can be broken up into a best rate of climb and a best angle of climb, which were found to be 15.5 degrees at a speed of 196.2 knots. And finally, the table at the right tabulates other supplemental V speeds that were found. And it's important to note that these calculations were performed using standard day conditions at maximum takeoff weight, with the exception of the glide speed that was found at 75% of the maximum takeoff weight. And now I'll be passing it over to Carlos for cost analysis.
Hello, everyone. My name is Carlos Bello, and now I'll be transitioning into the cost assessment of our Phoenix tanker, including our development cost, final sale price point, and our operational cost per year. So go ahead to the next slide. So the first thing we want to take into consideration when making the final price point of the Phoenix tanker were to include our material, labor hours, machine hours, and our engine production costs. So following all the integration, manufacturing, and everything that I just previously mentioned, we decided that the best price point for the Phoenix tanker would come out to approximately $183.5 million. And then this price point we can compare to some of these other comparison aircrafts that we had for our payloads, the 737-300, the C-130, the DC-10, and the 747-8. But one thing that we do need to note is that these prices are for the aircrafts without including the cost to convert these for the purpose of these missions, which would incur about a cost of $20 million per aircraft. Go to the next slide. So once analyzing the original price point of the Phoenix tanker, we can go into the operational cost to basically run this aircraft per year. And these are all associated with the full operation of the Phoenix tanker for different ranges of yearly usages, which can be seen in this table. Depending on the number of missions that the tanker endures or how many flight hours it's operational, this is going to differentiate between the fuel, the maintenance crew, the materials, depreciation, and insurance, which are all these factors that are going to be included in the yearly operation. And we estimate it's going to be about $27 to $43 million, depending on how many flight hours, which we're assuming 700 to 1,400 flight hours per year.
Thank you, Carlos. And with that, that concludes our presentation. And we're open to any questions that you all might have.
Thank you, guys. Great job. Let's ask question from our audience.
It was really good, wasn't it?
Hey, this is Joel Ligeti from Northrop Grumman. I really enjoyed your presentations, and I don't always say that to groups, just so you know. At the very beginning, your initial system slides showed a good understanding of the problem. You went beyond what the requirements were and said, hey, we did some analysis and we see all this other stuff that we needed to put into our design. So that was very good. Your presentation skills were excellent. And I saw your little thing at the bottom that told you which speaker to go to. That was a good way to do it. And your handoff to each speaker was pretty good. I have just some questions here. Let's see. I guess I think fair is fair. So can't detect my camera because I don't have it plugged in. Let's see. Slide 21. Showed your design selection and why you did it. The speaker talked about why they picked it. It might have been good to actually put those on the slide too, just because some of those are visual and some of people are reading slides. So it'd be good to capture both of those kinds of people in your audience, right? So you certainly covered the reasons why. It's just for those additional points, you might want to put it on the slides. Let's see. Slide 26 was very effective in showing that the requirements were met. You might want to go the extra point in 26 and actually show in green, which would have been all your actuals, just to kind of really cement in your customers' minds that you certainly met all the requirements. Just little tricks like that because you're selling your design in each of these things. On slide 29, you talked about the frames, stringers, and longerons being selected based upon a Boeing thing, but I would have liked to see some kind of analysis that showed that they were sufficient, that you did a stress analysis of some sort to actually show that that the design was sufficient. Not always are you going to have existing motors and engines and housing that are actually meeting or sufficient for the design. So you always want to go back and check that the initial design might have been deficient. Slide 43, I like that. Your center of gravity analysis was great. You looked at the whole mission rather than just saying, hey, for this spot in time, it was good and therefore it's good for all. But as you know, fuel shifts, you drop payloads, and then you got to figure out what do you need to do? Do you need to counter a change or a shift in your center of gravity? Slide 45, your stability slide. You talked about some of these things, and you said your aircraft was stable. It would have been good to see some kind of graph or analysis that showed your envelopes are for your stability, just so we know, because that's going to be important later on, because your customers are going to do all sorts of things to your aircraft that are outside of what you want to do initially, and then they'll ask you what point is too much. And then my last comment, slide 53. You talked about the conversion cost and 50, sorry, was it 53? Probably 52, the one with all the aircraft on it. Yeah, that one. You said something about the conversion cost being or you assumed that conversion cost was going to be the same, I think, and that's something you might want to take into consideration because each aircraft has its quirks, and sometimes they might not have the bulkheads in the right place, or you have to do certain things. So the conversion cost might be different for a certain aircraft. All right, thank you. But I thought this was overall, and I really enjoyed the presentation. Thank you.
Thank you for all this info. It was really, really great. Thank you.
Yeah, thank you so much.
Thank you for the comments. Any other question from our audience?
Yeah, so this is Rick Miles, Northrop Grumman. There was a page where you did a finite element analysis. So it looked like it was a basic, simple wing structure, right? So I'm not sure you necessarily needed to go to the effort of doing a full-up FEM, but if you're going to do a full-up FEM, it's going to drive me to questions. How did you load up this in order to get those results for the FEM?
Yeah, so
you go ahead, Oscar. Okay. Yeah, so for the load conditions for that, it was an approximation using Shrek's method. So basically it was a discrete loads on the wing. So I believe we did we loaded 5 ribs along the wing based on the plot above. And that's essentially how we loaded it.
Okay, yeah, I guess I would just question whether or not it would be easier to just do a beam, the calculations using superposition, right?
Oh, yeah.
So, because that's usually the easiest way to model a wing is from a conceptual standpoint is just to treat it like a beam with point loads.
Okay.
Or distributed loading, either one. And then the other thing is your choice of materials. You chose 7010 and you chose 2024 T4. I'm all good with the 7075 T6 because that's usually pretty widely used and available. I would question though how easily it would be to procure 7010 and 2024. And then with the 2024, there's just some history there with potential corrosion concerns using that material on aircraft. So that would be another thing I would just caution you on. But I agree with Joel. Very well done presentation, and I really enjoyed it. Thanks.
Thank you.
Thank you. Any other question or comments from our audience?
Hi, this is Elise from Cummins. I just wanted to say again that it was a very good presentation. I liked your numbering at the bottom so you could see where we're at. And yeah, it was just really well organized. And I just had one question about the thrust requirements. Yeah, so on that one, what was the 5% margin from? Was that a requirement?
So yeah, there was no requirement. We just put a 5% margin sort of just as a little bit of a factor of safety, but there was no There were no requirements given for any margin for draws.
Okay. Yeah, okay, just wondering where that came from. Yeah, so yeah, thanks.
Thank you.
Thank you. So any other question from our audience?
Anyone want to know why it's called the Phoenix tanker? I don't know. I don't have an answer.
Okay. I guess they don't have any question. So I want to say really amazing job. I'm really proud of you guys. This is like, well, through the whole semester, your report is always the best. So I feel like in terms of presentation, in terms of the content, and also everything present in a very logical way, like from a big picture, like initial estimation, design phase, analysis phase, and then from each topic, you put the like main thing you want to discuss at the front slides. It's like this is like the presentation I really want to like every group to present in this way. So so it's really amazing job. And there are some small things I'm just like curious about. So the first one is the balance field length. I just checked the requirement. I think the one the objective is 5,000 feet. So, and of course the mandatory requirement is 8,000. So what made you decide to like exceeding the objective 5,000?
Yeah, so because we couldn't meet all the objectives, we met all the requirements, but we couldn't meet all the objectives. There has to be trade-offs there. Because we went to a heavier payload tanker with the maximum, the objective 8,000 gallons of payload. We had to sacrifice somewhere, and that ended up happening in the balanced field length. So
Okay.
still well under the required, and we're about halfway between the requirement.
Sure. Thank you. And the next thing is the wait a second. I don't. So the power plant decision. I don't know the page number. Oh, okay. Page 19. Yes. So this one, I would consider that the value you put in the table, they are the score, right? It's not so.
Yeah.
I personally would prefer that. Well, of course, in the end, when we need to compare, we need to put a score for each term and put a weight for each term and calculate a final score and choose the highest one. But I would prefer that you can put the original number there so we know what it actually is. Is because every group and every person have different way to score each performance, each parameter. And if I just see the score, it's like I don't see I feel like I don't see the real thing. So I would prefer that I know this is a lot of things on one table. You probably can like make a single slide for this table, and in the table like bypass ratio, what is the bypass ratio of each one, and then put a score next to it. And same thing for all the other ones, like the cost, what is the cost of each one and what's the score of each one, right? So and the page 30. So I think it's 31, sorry. So the lift concentrated on 5 ribs. So this is like how you apply loading condition in the FEA simulation, I guess.
Yeah, exactly.
Why you consider to do it in that way?
So like Mr. Miles said before, it's probably better to do a distributed load. To give you the honest reason is SolidWorks would crash every time I try to do a distributed load. Yeah.
Okay.
So that was a workaround. And that's also why we trust our like mechanics and material results better, because just for this reason, I wasn't able to apply it as well.
Okay. I was just curious, like why 5 ribs? So well, another solution that if the SolidWorks crashes, you can choose. So there are like specific software for FEA analysis. SolidWorks is not designed for FEA analysis. Yeah. Well, this is, I consider the extra thing you did for the task, because the requirement of this class is hand calculation and FEA is not required. So it's fine. And the fuselage design 30, because I'm using the slides you upload on Canvas, so the page number is a little different. The fineness ratio 16.5. I feel this is a little bit higher than the regular fineness ratio range. Is it?
That was the diameter is 16.5 and the fineness ratio is 8.
Oh, okay. Sorry, my mistake. I feel like, okay, the fineness ratio is
that may have been a bad formatting.
And my mistake.
You're good.
And the on page, I guess it should be 51, because on my slides it's 50. Okay, the previous one. Yes. So you talk about different speed and you have a table to list everything. And when I see this table, you have VA, VC, VD, VG, NE, NO, R, S, S, XY. I mean, I don't know what it is. You know what I mean?
Yeah, we should have included a table to say like what they were. They're just like FAA regulated. So I don't know, it got a little cluttered.
Yeah, I feel like if it's something you can make sure that the audience can accept information you put in the presentation. If something that causes confusion or is some information that audience cannot receive, it's just no point, right? It just causes too much confusion. We don't need to make our presentation complete. There's no way we can make our presentation complete. We just using the 30 minutes to do whatever we can and make it like maximum communication efficiency. And I think that those are all the things I want to comment on. Again, great job, everyone. And let's see if anybody else had any question. This is the last presentation of our aircraft design today. Dr. Trump. Okay, I guess he's not here. He's busy. I'm
here. I'm just fighting Zoom and losing.
Okay, we're waiting for your comment on our last presentation for aircraft design.
Oh, am I allowed to ask them the entropy question?
You can ask any question you want.
Oh, okay. Well, normally I reserve this for mechanical engineers, and I'll probably ask the mechanical engineers this afternoon anyway, but how much entropy does your airplane produce?
More than one.
More than what?
Like a ballpark guesstimate. I mean, anyone have any guesses? There's a lot of fuel in there. I don't know.
Maybe a more fair question is how would you determine that if you had to? And I should tell you that the inspiration for this question is back 1,000 years ago when I was at the University of North Texas. I actually asked that on a final exam of my thermodynamics course. Not how much entropy does your airplane produce, but how much entropy does the University of North Texas produce? And it turns out, at least at UNT, there was a way to find the answer and the student should have known it. So that's always the last question that I ask in capstone design every semester. How much entropy did your system produce?
I think for the entropy, it puts a lot of order into at least the forest.
That's an interesting thought because, yeah, I would imagine a fire has a higher entropy than an extinguished fire. So, how about just the engines, right? You guys have got a couple of engines on your airplane. How much entropy do they produce? Uh-oh.
Yeah, not 100% sure on that answer.
Yeah, I don't think we're very confident in that question.
You can answer in any way you want.
Oh, okay.
Yeah, and to be fair, it's a highly theoretical question. Like, there's no practical application to how much entropy your plane produces. It's more of a, where you paid attention to the very, very nuanced bits and pieces of thermo.
I guess now's the time to say no. I'm just kidding. No, okay. So a good guesstimate. I guess let's go to our engine slide. Let's think about this.
I mean, it would kind of be dependent on the thrust that we produce, I would think.
I like that answer.
Well, I'll let you guys think about it. I'm actually, Dr. Chesney is texting me and asking me where I am because I'm supposed to be in the mechanical capstone presentation that started 2 minutes ago. So maybe maybe if you guys come up with a solution, you could email it to Professor Dong and she can forward it to me and I can check it to see if it's right.
100%. We will absolutely do that.
Yeah,
Okay.
we can do that.
Okay, it can, the analysis can be done, right? It's not like so, it's an esoteric question, but it's not so abstract and outlandish that the analysis cannot be done. It's just in a first law focused world, which, we're all in, mechanical engineers as well as aerospace. We all think about the first law and forget often about the second law because we're all into power generation. But 1,000 years ago, when I was a grad student, I worked in cryogenics, and in cryogenics, entropy is the master. It rules everything. And so we had to think an awful lot about how much entropy our systems were producing so that we didn't, instead of making refrigerators, if we messed up with the entropy, we made heaters. So anyway, I'll leave you guys alone. But yeah, if you've got extra time and bandwidth, I'd be interested to see that analysis.
We'll do.
All right.
Thank you, Dr. Trump.
Yeah, sorry, I got to run.
Thank you.